Let's talk about the attenuation of X-ray. If you remember in the previous a few videos back, we also talk about attenuation for signal, for optical fiber signal as well. And in fact, there is an equation you may find in the textbook right here that is same. I mean, not same, like it's literally the same as the one that we have in optical fiber. However, here there's also another equation which tells you the gray, should I say, the attenuation situation, how it has been less and less over the certain distance. And in fact, if you try to look at the form of formula right here, you will find that it will be extremely similar to what you have in all sort of exponential equation. For example, when you talk about in capacitor, we talk about maybe for the voltage, it would be less and less, and that there will be a equation like this, if you remember that. So the whole idea is very simple. Or you can also talk about the particle physics, the radioactivity. We also have an equation something like this. Alright, and again, the whole idea is more about the coefficient here. Okay, and the idea is almost the same. However, when you try to look at the study guide, you may want to find the relevant guideline. What you need to know exactly is last video we talked about sharpness and contrast, but we haven't got the time to talk about things like this. So in your study guide, it says attenuation coefficient, half a value thickness, linear / mass absorption coefficient, and you know, all these words looks like very specific terminology. So let's try to clarify that first. Okay, so first of all, we see that I mean, this is the equation of attenuation, and I think it's very self-explanatory. And one thing that you may notice here is something called the HVT, half thickness value. And if you try to compare that with what you learned in particle physics, this is basically half-life. Alright, half-life. And so that is the value of thickness. But of course, for half-life, it's talking about the time that it decreased to half. But here is the thickness that it decreased to half. So basically, it's the exact same thing. And therefore, in your data booklet, you may find the third equation here, or let me write bigger, mu x half equals to log, natural log 2, is the same way that how you derive the half-life equation as well. Let's take a look of this question. Try to use the equation that you just learned. Pause the video and we will check the answer. Okay, so it's a very simple example. So from the question, they tell you the thickness. So this one is basically x, and it also tells you that the half value thickness is 3 mm. So this is x half. You may want to put a symbol next to it. And they ask you to calculate the fraction of intensity get transmitted through the sheet. So there are two equations that you can use. So once again, in the equation, I mean in the data booklets, there are a few for you to use, and you have to use two of them here. The first one is the attenuation equation, and the other one is half value thickness, that equation. And what you simply have to do is simply substitute the things that you know, and you should be able to find the answer. And first of all, the first equation you should get in touch with is actually this one, and then you substitute 3 into this, and you find out basically the coefficient. And you basically what you have to do is to substitute these coefficient back here together with x, which is known as 4 mm, and you should be able to find the answer. And since it asks you about the fraction of intensity get transmitted through it, that means what has been remaining. Okay, so simply it's 40% in this case, which is I over I log. Very simple question. And if you try to continue to read the textbook, they tell you only very tiny stuff before they move on to the next part, which is about ultrasonic, I believe. And basically what the textbook tell you is saying that there is an equation, and what happened is when the material, the absorbent, got different density, then the coefficient of attenuation is different for X-ray. And because of that, we try to define and try to take away the idea of density to unify the coefficient. So simply to taking away the idea of density is simply by dividing it by density, and therefore the density would not matter, or we should say unified in that case. So this is called mass absorption coefficient, and it's simply calculated like this. And to be honest, I don't think this is a very good way to understand. I mean, this is not simply not enough information to understand the idea. And again, if you try to look at the study guide, I do really think it's very confusing. Like, what are they talking about? Attenuation coefficient. I mean, half fatal thickness is fine, but what's the difference between the word attenuation coefficient, linear / mass absorption coefficient? Are they referring that these two, mass and linear absorption coefficient, the same thing, or not? And also, is the attenuation coefficient different from these two? And the answer is actually quite counterintuitive. Okay, so let me try to clarify with you right now. Okay, so the first thing that you have to realize by looking at this, I mean, I personally do think they should rewrite this part. Attenuation coefficient actually equal to linear. Okay, so whatever they got, they say the attenuation coefficient, actually it's equal to linear absorption coefficient. Okay, it's exactly the same thing, and basically that equals to the mu that just now we talk about in the equation here, right? As you can see, they also said mu is the constant called attenuation coefficient, and that is the linear absorption coefficient as well. All right, because here what you have is basically the mu here. So this one is the coefficient that we talk about, and also it's called the linear absorption absorption coefficient. And after you divide by density, then this is the other one called the mass absorption coefficient, which is the one that we highlight here. Okay, so I don't know why they put a slash while the fact that they are not the same thing. All right, I will put the slash away, and I would not mention attenuation coefficient if I'm the one writing this study guide. I would just say linear absorption coefficient and mass absorption coefficient, right? While they are two different things. At the same time, the reason why I understand this more clearly is that I always ask you to try to read different textbooks, different sources, and to cross-check each other. So what I will recommend you to do is try to read Cognitive, which is also a pretty good source, and I also try to Google as well. Okay, so I'm trying to show you what I find there. So first of all, attenuation, you can see this is from Cognitive apparently. You can also see this equation, and the idea of this equation basically is also try to get the X-ray attenuation in the decibel scale. Alright, so basically the log scale. And I think the way to handle this kind of question or equations are very similar to what we learned, so we don't actually have much examples here. And now for linear and mass attenuation coefficient, see, this is a better way to say it. Alright, they are not the same thing and they are different things. So first of all, as we actually know, things like the bone, which is mainly calcium, with atomic number of 20, is much denser than other things like carbon, right? 6. So here then we can illustrate how a large Z atomic number would make the X-ray harder to penetrate through. So simply you can imagine the atom are bigger, and therefore if those X-ray with the idea of photoelectric effect, that means they are not just a beam of wave. I mean, it should be, I should say it's not wave but a beam of photon, which is particle. And when they try to get through these bunch of large atoms, then some of them will transfer the energy to the atoms, and that means the X-ray will lose energy. While for this one, which is less dense, the X-ray radiation can get through it more easily. So that's why the attenuation value will be different. And of course, for a smaller atom, it will be easier to go through, and hence a less attenuation number. Okay, so here is very clearly that mu is the linear attenuation coefficient, and then it said the value actually depends on the material, which is about the density and atomic number, and at the same time the energy of the photons. Okay, so the energy of the photon actually matters also, and as like how we perceive and understood from the textbook, the mass attenuation coefficient is simply the linear one divided by the density of the material. So you can see the unit is cm squared per gram per gram. Simply you can try to work out the units. Speaking of units, actually think about what's the unit of mu in the equation, right? In this equation, so let me write again: I equals to I log E negative mu x. What's the unit of mu then? Let me give you 3 seconds, think about it. The answer is, you can try, firstly you can see that I is here and I log is here. Apparently they are the same unit. They have to be the same unit. And here, in that case, that means E to the power of this whole thing has actually no unit, because this is like a ratio or like a coefficient as a whole. Or you can imagine this is like the probability multiply with the original one, and then you get the final one. Okay, so this whole thing is dimensionless, and to get the dimensionless number, then this index has to be dimensionless also. While x is thickness, which may be in the unit of millimeter or cm, then mu has to be millimeter negative 1 in that case. So that is the unit of the linear coefficient. And so back here, then you may be able to work out by dividing the density unit by yourself. Okay, so this is how you can do it. Here, there is a really good picture from Cognity that you can see for photon energy with a higher energy. Then you can see that the attenuation is getting less and less and less. Right, this is attenuation for the mass coefficient. So firstly, of course, you can see for different density it will be different, but eventually it's more or less the same, because in fact, I mean, this is simply just what we observe in experiment. I don't think we have to remember the result, but what you have to understand is, like we said, for different energy of X-ray, since if you remember we can apply a higher voltage, then X-ray will be of higher intensity. And then in that case, apparently imagine you got more energy at the beginning, then of course more can pass through it, so the attenuation rate will be less in that case. So that's why it gets lower here. And as we said about the density, then that would be shown on the graph here instead. Okay, and I think that's pretty much from Cognity. I also try to look up on Google, and I try to find something more, and all these coincide to what we talk about. And if you're interested, try to find the link in the description and find some more website like this one. As you can see, mass attenuation and how to convert to linear is like what we did, divide by density. Here's another picture of graph obtained from the experiment, and you can see things like lead, the green one here, and tungsten, the one that you use for light bulb, would be of a really high attenuation coefficient, while things like silicon is not as high. All right, and also when energy increases, then attenuation will be less in that case. Same for Wikipedia, although it's not the best source of cite. You can see basically the same thing that we have mentioned. Okay, so I think the lesson we learned here is really not just stick with one textbook, as you know, there's not much things here, and also try to clarify what has been written by the guideline. Is it really clear enough or not? Okay. So yeah, that's basically what I said. So right now I think it's almost time. Oh, by the way, one more thing from quantity is if you have multiple layers, then you can simply try to get the coefficient around together, and that is the best part of how we have that equation set up at the first place, like how we set up this. And then the best is you can put the coefficient all together for like very simple computation. Okay, so if you're okay with what we said, try to do this question in your textbook. You may want to pause the video first. Okay, so from your questions, you should be able to find the half value thickness from the graph, and basically you can see it start from 100%. So let's try to locate 50, which is half. So 1, 2, 3, 4, 5, which is right here, and then you simply draw a line. Alright, forgive me if I didn't do it very well, and it's around here, this line. And same if you go for another line, and it's about here. Okay, so from what I see, it should be for this line, it should be for A, I should say. This one I name it as A, this one I name it as B. For A is 6.2 millimeter, while for B is about 3.8 millimeter. Alright, for the half value thickness. Very simple. Part B, asking you which one corresponds to X-ray with high energy. So if you remember, the higher energy should have a less attenuation, so it can go through more quickly. So it should have, in that case, have a higher half thickness, right? Imagine that, right? This is a piece of lead or whatever, and then with low energy, it would take, like, imagine just like shall we say bullet. Right, if you shoot a bullet really low speed, however, low speed of bullet really versus a fast speed bullet, the fast speed bullet can go through a thicker distance, right? Because it simply carry more energy in that case. Okay, let's try the next question. Pause the video now. Okay. So very similar stuff like the last question. First, the question asks you to determine the value of attenuation coefficient, and what you have to do is, again, once you are given the graph, I think one thing that you must find as given or hidden information is looking at its half intensity, which is 50%, to find the half thickness, which is about 5 millimeter. Okay, for here. And so what you could do is there's an equation about half thickness, which of course if you don't remember, you can find a data booklet, or even you can prove it, and then you should be able to express in numbers the linear coefficient, attenuation coefficient, which is this one. And once again, you should put down the unit, millimeter -1, if this is in your exam. For part B, it asks you, so what is the thickness so that it will reduce the transmitted intensity by, okay, be careful, by 80%. So be very careful with the word here, by 80% or to 80%, that will make a huge difference. So by 80% means you only have to remaining 20%. So that's why I do 1 minus 0.8, 100% minus 80% here. Okay, but for the rest are very easy. You just have to use the other equation, the attenuation equation, and you substitute the mu you get from part A into this, and again on the other side you have I over I log. That will be the ratio of the remaining. All right, always remember this is remain, what has been remained. So that's why 20% is the remaining one, and you substitute and you find the answer, 12 mm in that case. Try the next question, pause the video. Okay, so again, very similar stuff like the previous question. So what it said is, again, it said reduced by, again, by 40%. So that means remaining is 1 minus 0.4, which is 0.6, which is 60%. And you could substitute 4 mm, which is a thickness, to find out the value of mu, the attenuation coefficient, once again. And afterwards, the question asks you, so again, how much is required to reduce by 80%? So I think it's very similar to the previous question. This is the last question. Pause the video now. Okay, so for this question, I think I will talk about part B first. Okay, so it said there are two kinds of X-ray energy, and then each of them will have a different value of half value thickness. And so now it asks you, what if you have the absorbance or absorber to be 5 mm, and what is the ratio of that two being transmitted? So the first thing that you want to do is again to find out the attenuation coefficient, like so, and you refer, after you obtain that, you refer to again this equation. And since now you have two and you want to find the ratio, so you imagine you substitute each of these to this equation separately, and then you simply divide them since you want to find the ratio. So I will put the subscript nicely, so try to use your subscript more nicely, which is I25 representing 25 keV over the I20, which is 20 keV. All right, on the right hand side of the equations, then you simply substitute the mu, which you find, and x, which is 5 mm, into it. And I think the rest is simply, I mean, of course these two will cancel out, and then whatever left is simply the index with minus, since this is a fraction. So you simply have what I do is I taken out the -5 outside, and then the two index will minus each other, and you simply find the final answer by your calculator. Okay, so the ratio is actually about 1.4 in that case. Okay, so apparently the higher energy X-ray would have a greater intensity afterwards, and I think that is quite intuitive in that case. All right, even though we cannot do any experiment. Part A is asking you to suggest what it means by the X-ray that is not monoenergetic, and why is it harder, we call it harder for these beams, as they are allowed to pass through material. I think the basic idea is, since you have different energy, I don't think, I mean, the way that it said is a very nice way to say like what it means by actually hard. I don't actually know. But what I could say about it is, when you try to mix two different energy, like here 20 and 25 keV, and when you try to apply it to a certain thing that you want to test, you want to see how thick they are, mixing two energy would help you to see a more distinguished result. Because in that case, you may find 20K has already been, shall we say, decay, or the energy has been reduced a lot, while 25 did not, right? So it may help you to see a wider a more contrast picture in that case. I think that's what I can talk about for how, like, the advantage of mixing, having multi-energy in the X-ray. That's all for the X-ray attenuation.